Hello everyone, welcome back to my YouTube channel. In continuation with the last lecture on point defects, let us today see the equilibrium concentrations of Frenkel and Schottky defect. So, let us first consider the Frenkel defect. So, what is a Frenkel defect basically? It is a kind of point defect, that is, it is basically a defect related to one or two atomic diameters, and it occurs in ionic crystals. It majorly occurs in ionic crystals and ceramics as well. Okay, so what is a Frenkel defect then? So it happens when a cation moves from lattice site to an interstitial site. So a cation leaves its lattice site and moves to an interstitial site. Interstitial is the site that lies between the lattice points actually. And why is it that only the cation moves? It is because the cations are smaller and they can easily accommodate, being smaller, they can easily accommodate in the interstitial sites or the voids. Okay, a bigger atom or a bigger ion takes up way more space than a smaller one and also induces stresses while it tries to accommodate in a smaller space. So, but there are instances where anion can also move to an interstitial site. So, when anion moves to an interstitial site, then it is termed as an anti-Frenkel defect. Then it isn't a Frenkel defect but an anti-Frenkel defect. Alright. So understand the difference between a Frenkel defect and an anti-Frenkel defect. But usually being bigger in size, this doesn't move in usual cases. Okay. So we can easily conclude that Frenkel defect is equals to a cation vacancy as it leaves its lattice site plus a cation interstitial as it goes and occupies an interstitial site. So, what will be the total number of configurations of defects, or the number of configurations in which defects can be arranged? That becomes equal to total number of ways cation vacancy can be arranged multiplied by total number of ways in which cation interstitial can be arranged. Okay, so ways of arranging a cationic vacancy multiplied by ways of arranging a cationic interstitial. So this gives you the total number of configurations in which the defects can be arranged. So let us check out the Gibbs free energy change. So delta G becomes, from the previous derivation of point defects, you can see N Fp of a Frenkel pair, delta HF, delta enthalpy of formation of Frenkel pair minus T delta entropy of formation of Frenkel pair minus Boltzmann constant into temperature into logarithm of n plus nv, that is number of vacancy, upon nv factorial into n factorial plus ln n plus ni, that is number of interstitials, n factorial into ni factorial. So we say n is equals to nv equals to ni, since the number of vacancy and the interstitial will be equal, because as many cations leave the lattice sites, that many only are available at the interstitial sites. So they become equal. That Frenkel defect always occurs in pair. So from this we can say delta G is equals to number of Frenkel pairs into delta HF minus T delta SF minus KBT. So ln n plus small n factorial divided by n factorial plus ln n plus small n factorial divided by capital N factorial into small n factorial. So this becomes delta G is equals to number of Frenkel pairs to delta HF minus T delta SF minus 2 kBT ln n plus small n factorial divided by n factorial into small n factorial. So to see the equilibrium number of Frenkel pair defects, we differentiate this delta G with respect to n. So del of delta G by del n, this becomes, so delta HF Fp minus T delta SF Fp minus 2 kBT del by del n into ln n plus n factorial divided by capital N factorial into small n factorial. Okay. Now differentiating this last term on the right, that is del by del n ln of n plus n divided by n factorial. So using Stirling's approximation, let this be equals to capital A. So using Stirling's approximation, we can write A is equals to del by del n. So this is n plus n into ln n plus n minus n plus n minus n ln n minus n minus n ln n minus n. Since as per as Stirling's approximation, ln of x factorial is x ln x minus x. So now this cancels out, this and cancels with this. So what we are left with is A is equals to del by del n of n plus n ln n plus n minus n ln n minus n ln n. So let us differentiate first term. So it becomes n by capital N by n plus n plus ln n plus n plus n by n plus n. So this is a constant with respect to small n, so it will be 0 minus ln n plus n by n. So this term and this term, they add up to give 1 plus ln n plus n minus ln n minus 1. So this cancels out and it becomes ln n plus n by small n. And since n plus n is almost equivalent to n, this becomes ln capital N by n I. So using this in the equation, this one, we get del of delta G by del N is equals to delta HF minus T delta SF plus minus 2 kb T ln n by n I. So this becomes del of delta G by del N is equals to delta HF minus T delta SF plus 2 kb T ln Ni by N. So now for this to be at a maximum, it should be equal to, the derivative should be 0. So this becomes 2 kb T ln Ni by capital N is equals to minus delta HF plus T delta SF. So ln Ni by N is minus delta HF by 2 kb T plus delta SF by 2 kb. So Ni by N is equals to exponential of minus delta H F F P by 2 kb T into exponential of delta S F F P by 2 kb. So this is the equilibrium fraction of Frenkel pair defect. So it can be number of Frenkel pairs by lattice sites is equals to exponential minus delta HF FP by 2 kBT exponential delta SF FP by 2 kb. This is the final expression for equilibrium fraction of Frenkel pair defect. Okay. Now, when Ni is not equals to n, this NFP by n, this becomes number of interstitial sites by n under root, then exponential minus delta HF FP by 2 kBT to exponential delta SF FP by 2 kb. Okay. So these are the expressions for Frenkel pair defects. Now next is Schottky defect. So what is a Schottky defect? So basically it is a pair of vacant cation and anion. So it should always be made sure that a cationic species and an anionic species both are missing for the same charge, and necessarily charge neutrality should be maintained. Okay, so if a cation of +2 charge is missing and the anion has a -1 charge, then two anions of -1 charge should go missing. Okay, so the missing charges of both positive and negative should always be equal. So similar to the Frenkel defect, number of ways, total number of ways of defects, they can be total number of ways cation vacancy can be arranged multiplied by total number of ways anion vacancy can be arranged. Okay, so this results in an expression of delta S configuration, that is KB ln omega. So that omega is n plus nc factorial divided by n factorial into nc factorial into n plus n a factorial divided by n factorial into n a factorial. Now here nc is equals to na, assuming both anion and cation are having the same magnitude of charge. Okay, so then if this is n, so then delta S configuration as derived for Frenkel pair becomes 2kb ln n plus n factorial divided by n factorial into n factorial. So then the equilibrium fraction of Schottky defects becomes nc by n is equals to na by n, and that is equals to exponential minus delta hf for Schottky by 2kbt into exponential delta sf Schottky by 2kb. This is the expression for equilibrium fraction of Schottky pair defect. Okay, so this was about the mathematical expressions for equilibrium fraction of different types of point defects. Thank you.